We have just seen a particularly interesting interpolator, namely the sinc function. We will now study this in more detail. We take an arbitrary sequence, we interpolate it using the sinc interpolator, and we will see the result is necessarily a band-limited function. Now, this band-limited function belongs to a subspace, the subspace of band-limited functions, and we'll be able to prove the fundamental result, the sampling theorem, which says that by taking uniformly spaced samples on the space of functions that are band-limited, we can perfectly reconstruct them.
Module 6.3. The space of band-limited signals. The overview of the submodule is that first we look at the spectrum of interpolated signals, in particular interpolated by the sinc function. This generates the space of band-limited functions, or BL. Then we will be able to show sinc sampling, and this naturally leads to the sampling theorem, one of the most fundamental results we are going to see in this class. The ingredients of sinc interpolation are a discrete time signal xn with a DTFT capital X of e to the j omega, an interpolation interval ts, which will set the distance between samples that we interpolate, and the sinc function properly scaled to have zero crossings at multiples of ts. The result will be a smooth continuous time signal x of t, and the question is, what is the spectrum of x of t? Recall key facts about the sinc function. So phi of t is sinc of t over ts. Ts is the sampling interval, pi over capital omega n. Its Fourier transform, we know, is a rect function, properly scaled, and omega n is just the reverse, it's pi over ts. It is much nicer to see this in pictures, so on the top you have the time domain function, it is 1 at the origin, and at all multiples of ts it has zero crossings, and the Fourier transform of phi of t is the box function between minus omega n to omega n, and properly scaled and height to pi over capital omega n. The sinc interpolation we had seen before. You take the sequence xn, you multiply each term xn with the sinc function centered at the location n times ts, and the result x of t is simply the sum of all these terms. So what is the spectrum of this interpolated signal? So let's compute the Fourier transform, capital X j omega, which is the integral of x of t multiplied by e to the minus j omega t. We write out the expression for xt as the interpolation of the sequence xn. Then we interchange the order of summation and integral. We can take xn outside. So inside we have sinc of t minus nts over ts. Then we remember, of course, that the Fourier transform of sinc is a rect function. But it's also sinc shifted by nts. This gives a phase factor e to the minus j nts omega, which is at the very end. Let's analyze this formula in detail. Capital X j omega, the Fourier transform of our sinc interpolated signal, is the summation here of xn times the rec and e to the minus j n ts omega. The rect function does not depend on small n, so we can take it in front. We are left on the right side with the summation from minus infinity plus infinity xn e to the minus j pi over capital omega capital N times omega, the variable, times n. Now we recognize an old friend. This is a discrete time Fourier transform of xn, the sequence, rescaled by 2 times capital omega capital N. Now this DTFT is periodic, and the period is 2 times capital omega capital N. However, it's multiplied by the rect function, which takes away all the repetition except the central one. That's what we see in the last equation. So the Fourier transform of x of t is equal to a scaled version of the DTFT of the sequence between minus capital omega n and capital omega n, and it is 0 otherwise. It is best to look at this in a figure. So on top you have the DTFT of the sequence xn. This is a 2 pi periodic function. We show the central period from minus pi to pi. The Fourier transform of x of t, the interpolated version with a sampling interval of ts, is a scaled version, and it lives between minus capital omega n and capital omega n. It has the same shape as a DTFT, simply it is rescaled along the horizontal axis to fit on the interval of length 2 omega n. What happens if we change the sampling interval? So for example, let's space the samples twice apart, then the spectrum will be sharpened and it will live between minus omega n over 2 and omega n over 2, or if we take a sampling interval which is half of the one that we had seen at the beginning, Ts over 2, then it will broaden the spectrum which now lives between minus 2 omega n and 2 omega n. The intuition is simple. If the samples are spread apart, the function becomes slower. If the samples are closer together, the signal becomes faster. Let us summarize this important point. So when you pick the interpolation period Ts, the interpolated signal has a omega n band-limited spectrum, where omega n is pi over Ts. So with fast interpolation, when Ts is small, the spectrum will be wide, and when you do slow interpolation, so Ts is large, then the spectrum will be narrow. In some sense, it's like changing the speed of a record player. We have seen that starting with a sequence in L2 of z, through interpolation with a sampling interval of Ts, we get x of t, a band-limited signal, namely band-limited to omega n. This function x of t is uniquely specified by the sequence xn. So an intriguing question is to find out if we can take samples of xt and get a sequence again that is uniquely specified, and so we have a one-to-one relationship between sequences and band-limited functions. The answer to this question is actually positive, and it's given by the sampling theorem that we will see in a moment. To make our life easier, we are going to pick Ts equal to 1, which means that omega n is equal to pi. The general derivation is given in the book. We make a couple of claims now. The space of pi band-limited functions is a Hilbert space. The set of functions phi n of t, which are simply the sinc functions shifted to location n, form an orthogonal basis for that Hilbert space, and if x of t is pi band-limited, then the sequence of samples xn is a sufficient representation. In other words, if we have the samples xn, we can reconstruct xt perfectly, and that's the essence of the sampling theorem. So the space of pi band-limited functions is a vector space. It's a subspace of L2 of R. This we shall not prove, but it is intuitive, because if you add two band-limited functions, the result will be a band-limited function. So that's the closure of the vector space. The inner product is the standard inner product in L2 of R, and the completeness issue, which is of course the trickier one, is more delicate, and we'll not address it here. Just remember the definition of the inner product and the fact that the convolution can be written as inner product, just taking care that we do the change of variable t minus tau in one of the two elements of the convolution. Let us prove that the sinc function and its shifts by integer is an orthonormal basis for the pi band-limited space. For this, we need to show that the inner product between phi n and phi m is going to be equal to 1 when n is equal to m and 0 otherwise. So let's write this inner product between phi n and phi m. We can see that's the same as between phi 0 and shifts of t minus n and t minus m. Then we use the fact that the sinc function is symmetric in this argument, so t minus m can be changed into m minus t. Therefore, we have the integral of sinc t minus n, sinc m minus t dt. This we can factor as the convolution of two sinc functions shifted by m minus n. Now we can use the convolution theorem, knowing that the Fourier transform of the sinc function is a rect function. So think convolved with think at location m minus n is 1 over 2 pi the integral of rect square, and then e to the j omega m minus n d omega. This is simply the integral over minus pi to pi of this function that we have seen before, and this is equal to 1 when m is equal to n, 0 otherwise. With this, we have shown that Sinc functions are orthogonal to each other when shifted by integers, and the sinc function itself is of norm 1. So we have an orthonormal set of vectors in BL of pi. This set of orthonormal vectors can be shown to be an orthonormal basis for band-limited functions. To see sampling as an orthonormal expansion, we take our set of orthonormal vectors, phi n, take inner products with x, and we look what comes out. So write this as sinc t minus n inner product with xt. We use symmetry again, and then this is a convolution of sinc with x at location n. Now use the convolution theorem. So this convolution of sinc with x is a product of rect with the Fourier transform of x. We take the inverse Fourier transform of this product. That's 1 over 2 pi the integral x e to the j omega n d omega. And this, of course, is exactly equal to xn. So the inner product between phi n and xt is simply the sample of x at location n. We have now the coefficients of the orthonormal expansion, that's xn, the samples, which is the inner product between sinc and xt, and this gives us the synthesis formula in an orthonormal expansion, namely x of t is simply the sum xn sinc of t minus n. Not all band-limited functions are precisely band-limited to minus pi to pi. So what happens to omega n band-limited functions? Well, we will need to rescale the sinc function by ts. Ts is equal to pi over capital omega n. And with this rescaled sinc, we have an orthonormal basis for the set of omega n band-limited functions. The formulas are given here both for analysis, how to sample inner product between sinc and the function, and the synthesis formula, the linear combination of xn times the rescaled sinc function. We can now conclude on the sampling theorem. We have seen that the space of omega n band-limited function is a Hilbert space. We can set Ts is equal to pi over omega n. The functions phi n, properly rescaled, form a basis for that space, and any xn belonging to the space of band-limited functions has coefficients in the sinc basis that are simply given by the samples. So in conclusion, for any xt which is in omega n band-limited space, a sufficient representation is a sequence xn is equal to xn of ts. A band-limited space is always a subspace of another band-limited space that has a wider bandwidth. This also means that if we have xt that belongs to omega n band-limited, a sufficient representation is the sequence taken at multiples of ts for any ts that is smaller or equal to pi over capital omega n. So when we take more samples than necessary, then this is something that is called oversampling, that we are going to see again when we talk about practical analog to digital conversion and sampling. Maybe this is a good point to describe the sampling theorem in terms of hertz frequencies. So any signal xt band-limited to fn in hertz can be sampled with no loss of information by using a sampling frequency fs greater or equal to 2 times fn. Fn is the so-called Nyquist frequency, that's the maximum frequency present in the signal. Or the sampling period ts has to be smaller or equal to 1 over 2 times fn. To make a concrete example, speech over telephone lines is typically band-limited to less than 4000 Hz. Therefore, digital telephony uses 8000 Hz sampling rate, which is a sufficient representation of speech and allows to reconstruct the speech at the other end of a telephone conversation adequately.